And we continue, where really the three speakers, Stefano, James, and Chris, are basically on the panel. And we should basically ask some general question. I mean, I was writing some down in the coffee break, but we could start really with a question which just Chris had, and saying, how can we really, I mean, the idea which we have in NORMAT is that we don't really say actually there are data, calculated data, which are good or bad. The question is only for what are they good? And I mean, there may be, say, things which you do with a not so good basis set, but they still will give a good geometry, but they will not give really a good, say, electronic response or something like this. So there should be really an identification in getting from the basis set and from the functional some idea for what are the data good, which then also means for what are they probably not so good. So this is actually what we are working on, but that is not really trivial. But any suggestions really more from Stefano or maybe James or Chris again would be good on that. So how should we qualify or quantify the accuracy or precision of these calculations?
Exactly. So what I would add there is that the challenge is mapping the uncertainty in input parameters through to the uncertainty in output observables, and often that's a very complex, non-linear process, and that's where I think a lot more effort needs to be invested on formalizing this uncertainty quantification task. So if we have a good idea of probability distributions of errors and input parameters, then it should be possible to propagate them through a solver and come up with probability distributions of outputs rather than point estimates. I think that's something that we should all try to do a bit more of.
Gianmarco has his hand up.
Yes. I don't know if we really need to quantify the error, because there's these, if we want to do machine learning, for instance, there are those multifidelity methods where all you want to know is that a bunch of data have the same quality. And so, for instance, you know, Chris was mentioning that all the input parameters are known for OQMD, and so you can say that all OQMD has the same kind of quality, whatever it is. Then you have another bunch of data which has another quality, and then you have the experimental data, which are supposed to be the ones that are perfect. And then if you use these multifidelity methods, you add a tag to the data in such a way that you know that this is coming from there, this is coming from there. And so the model is then, you know, predicting the data associated to a given tag. And so you know that you exploit everything to have the experimental one, which is supposed to be the correct one. So this might be a way to avoid, you know, quantifying the error in all the cases.
I think if I could chime in too, I think one thing that I've observed a number of times that maybe just came up is I've seen this happen many times where experimentalists ask DFT people about the uncertainty or the accuracy of DFT, and the DFT person responds by talking about K-points and basis sets. And so I think it's important that we sort of clarify, and whereas I think the original question had to do with the physical accuracy of DFT as a method. In other words, they wanted to know about exchange correlation. The response was about numerical precision of the calculation. And so I think we have to be kind of clear that these are two completely different things. You know, the numerical precision is just what you would get if you converged everything as well as you could. But that doesn't mean that the answer would be physically accurate. Right? That's a function of the approximations of the method itself. So somehow I think we actually need to address both of those issues, I guess I would say.
No, I fully agree. I think really, I think we need some quality mark which says actually this calculation, if it's an LDA calculation with a bad basis set, you don't say actually what it is, but you say actually this is still good for geometry, right? Of if you want an accuracy of whatever. But there is the accuracy, which means actually what exchange correlation function you are using. And then there is the precision, which is basis set or K-points and other numerical approximations. And somehow for the known, I mean, the experts have a feeling what that means, right? They know actually this calculation I can use for this, and it gives me good results. And but I shouldn't do this for this. But at the end, having a database and being fair, we should give the data to people who are not really the experts. And that's why I feel we need some type of labeling. This is good for this purpose, and this is good for another purpose, or this is good for every purpose. I don't know. I think we have to work on it, but it's a lot of work, I think.
Maybe we'll just add to that that labeling is very subjective and could become quite political if one starts labeling other people's calculations. So it has to be done very carefully with input from the whole community.
Stefano here. Can you hear me?
Yes.
Okay, so let me tell you what we are doing at AFLO. For a lot of same geometries have actually different directories in which we optimize for instance, for electronic structures, and then we use LDA plus U or similar, or for geometrical structures and results. And all this data and how to navigate is the part of the input file, which is included in JSON or aflolib.out, the post process. For what concerns, okay, second, we do calculations as with respect to the
actually now, Stefano, now you are very badly.
Gets a identifier. Oh, can you hear me?
Actually, you were pretty distorted the last sentence.
Okay, I said that we order the calculation not with respect to the material, but with respect to the output, because a single structure like sodium chloride could have many calculations. So we do not have a material 1, 2, 3, but we have a calculation 1, 2, 3, or calculation 4, 5, 6, and this is given by the unique identifier that we have introduced many years ago. Then for what concerns precisions, okay, precisions, it's part of the input, okay, numerical parameters. They are in the input file, and we can analyze them and see a posteriori which how many K points, what is the cutoff, etc., etc. But this still does not talk to the experimentalist. To talk to the experimentalist, we have created a method which is CCE, coordination corrected enthalpy, which corrects the enthalpies, if available, to the one that are experimentally available. And we are slowly populating the whole database of these corrected enthalpies. So if the corrected enthalpy is a part of the output, then these things can really be used for calculating enthalpies, reaction enthalpies, or estimating transition temperatures. So this is what we are slowly doing. And this is work that has been Corey Ozis and Rico Friedrich are doing mostly. And so we are progressing based on what is available. So yes, I agree with you that to talk to the experimentalist, it's a lot of work and it's going to take years, but I believe we are moving in that directions.
Okay, let me go a little bit further, but with the same philosophy, I would say. And let me actually just, I wanted to share.
Well, Matthias, if I could chime in one more thing,
Yeah.
and since you said we were supposed to say provocative things, so I'm about to.
Mm-hmm.
And that is that, I think we should also remember that experimental data is not perfect and has, inherent errors associated with it. And oftentimes these errors can be actually quite large. So that's one thing to keep in mind. And a related comment is that sometimes when we want to determine the accuracy of our methods, kind of from a statistical sense, we want to know kind of statistically how accurate is a certain property. In many cases, we don't have enough good experimental data to even answer that question. Yeah. And so that can be a very limiting thing as well.
No, I fully agree. And we can learn actually from the quantum chemistry, which says actually, if I want to check the accuracy, I probably actually better check against theory, because either actually the experimental data are, say, different because of defects or hydrogen, or in fact, they are different because they have electron-hole interaction, they have phonons and whatever, things which we don't have, right? So we want an accuracy within really the model, but then we want also the comparison with the experiment. So these are two issues, I think, which are very important.
Right, right.
And I think quantum chemistry has shown really what they have done, and I think we can learn a lot still from them.
Right, and I think in terms of the formation energies, we do kind of adopt a similar idea, right? That most of the databases, I'm pretty sure AFlow and OQMD and Materials Project all have these kind of elemental corrections associated with the chemical potentials of the elements that are essentially fit to experimental data. And if there's not enough experimental data or good experimental data, then we can't do that correction, and that actually becomes limiting quite quickly.
Yeah.
Chris,
I mean,
Chris, can I answer your questions?
Okay, yeah.
We do not have elemental, we have correction, but they're not elemental, because we believe that tilting the phase diagrams is actually thermodynamics incorrect. So our correction are based on coordination and oxidation states. They're not based on tilting the phase diagrams like FAIR methods or the oxygen correction method does. But that's okay. So we do have the correction, but they're not elemental tilting of the Gibbs free energy.
Okay.
Okay, so let me carry this question to a different level, which is my first thing here. And that is actually because we all talked about, I mean, James started much, but everyone else also mentioned machine learning. And if we want to really deal with all this enormous amount of materials, we have to do that. So the question is similar to what we just did with DFT in the discussion. What is the reliability of machine learned potentials or the machine learned models? Now, we all know that machine learning interpolates. In that sense, machine learning is very different to what density functional theory is actually aiming at. There we think we can describe whatever we want to describe if we have the right functional. But machine learning only interpolates. And so how do we know when a machine learning description becomes an unreliable extrapolation? Extrapolation, or it's really interpolation, extrapolation, not very well defined. So at some point, machine learning is running out of the fitting regime. And in physics, you usually call this domain of applicability. We know when Newton's law breaks down and so on. So what do we know? And that goes maybe to James and also to the other two. When do we know that really the models which we have, the potentials which we have created, are no longer reliable?
Yeah, I can start on that maybe. Thank you. That's a very good question. And maybe before turning specifically to potentials, I'll just add one more point at the DFT level. So in the same spirit, if you want to quantify the uncertainty in a calculation performed with DFT as a function of the unknown exchange correlation energy, then one way to do that would be to sample over possible choices for the exchange correlation energy. That's something we did a couple of years ago at the meta-GGA level. So sampling over possible expansions of the exchange energy. In that case, I think we fixed correlation, so we didn't tackle the whole problem. And that gives you not just prediction, but an ensemble of predictions, and gives you a statistical idea of how important the part that you're changing is for determining the quantity of interest. And I think that's exactly the spirit in which to approach the same question with machine learning potentials. So not to view a potential as a single model, but to view the collection of all the potentials that are compatible with the training data. And then you can get a much better idea of where all of those different models agree, and that's where you're interpolating, and where they start to disagree significantly, and that's where you're extrapolating. That's oversimplified, of course, but both neural network and kernel approaches have ways of generating these ensembles, and I think that's a straightforward way to start to quantify uncertainty. But maybe a broader point is that as a community, I think we need to move more to assessing these models on the quality of their predictions on physical properties, not just on test and training splits, etc. So we're really focusing on predicting real quantities that in principle could be compared with experiments. And then I think you have a much more valid basis for assessing when you're within the domain of applicability of the model and when you're at risk of straying outside it.
Yeah, thank you. Gianmarco?
So I think for your first question, right, it's just a matter of doing the machine learning correct, right? If you use Gaussian process regression, then the result of the machine learning will tell you how correct or how plausible the result is at that point, no?
Well,
you're right. I mean, Gaussian process has it, but neural networks typically does not have it, right?
Yeah, indeed. I mean, that's a problem with neural networks, I guess, right?
Can I maybe just add that both methods are capable of giving uncertainty estimates if they're used correctly, but they're often not. And even Gaussian processes, the error estimates are only reliable if you either optimize the hyperparameters or sample over different posterior draws that are compatible with the data. And nobody's really doing that yet in our community. They're just taking the central estimate and maybe the variance estimates, but they're often not calibrated at all. So I think that risks being an oversimplification.
Luca?
Yeah, James has essentially said one part of what I wanted to say. The other part is that the neural network have also the uncertainty estimation. This is called Bayesian neural networks. So it's a more recent technology, but it is one can demonstrate it is essentially doing the same as a Gaussian process kind of estimate. So on that side, they are equivalent, but they are equivalent in being limited by the fact that you have to assume that you have a distribution of data that is represented in your training data. Otherwise, it's I mean, it's not magic. It's not cannot give uncertainty on things that are completely different from what you've used for training. That's the bottom line. Yeah.
Yeah. So if there would be I mean, that's basically what I'm saying. So what is the range of applicability also means if there would be a phase transition, which in fact the training data didn't have in, right? I mean, the neural network can also not really find that, I guess. So related to that is the second question, which I put here is we're collecting data. Of course, in theory, we're collecting a lot of data. But if you would do the same machine learning things with experimental data, we would not have very many data in material science. And that is what is called the Bergson paradox, because what you find in machine learning is correlations. And the Bergson paradox says that if you basically have your selection of data and the selection of data has some bias, what you will learn is not the physics of the data or the science of the data, but you will learn the bias which you put in. A little bit, I felt I heard that can happen, right? I mean, also with the data which we have, that if your data are not complete, you will more or less really find something which does not necessarily make sense. Is there any experience with this subjective? I mean, we are always subjective in data production, right, or selection. Is there any experience with dangers of that?
I guess I could say one thing about that that I kind of tried to illustrate in my talk. So I said, one way you could imagine doing these high throughput searches is choose a crystal structure, decorate it with all possible combinations of elements, and calculate them all. I would categorize that as relatively unbiased. I mean, in the sense that you've calculated everything, you haven't sort of made any decision about which combinations to choose and so forth. And like I say, that's kind of what we did early on in OQMD, and it resulted in a lot of, very sort of diverse data sets that I think now are bearing a lot of fruit in terms of machine learning. Now I said what we're doing is actually using the data to train machine learning models and then use machine learning to decide which calculations should we do. We don't want to do them all anymore. We want to do only a subset of them. Now that's biased. That's strongly biased. And so, yeah, we are potentially running into that problem that, that we're going to more and more rely on machine learning to even decide which calculations we want to do. And I am a little bit worried about that we could be sort of running into this position where we're biasing the data that's telling us to do, and then we're never getting out of this loop. So I think definitely even if we get into this situation where we're generating machine learning models to tell us which calculation to do, I think we still need to every now and then just do everything in an unbiased way just to make sure we're not sort of running into this problem.
So we have 3 hands up. I think Gianmarco was the first, or maybe that someone else in Louvain, and then Luca, and then James.
Yeah, that's actually me. So I just wanted to share an experience in which, I mean, it's not always obvious to identify the kind of bias that you have. So we had a database in which we had the refractive index for 4,000 compounds. There were many oxides, so we feared that there was a bias towards oxides. And when we analyzed the data, actually, the bias was not there. There was bias, but it was not related to that. So the bias was more about which regions of the space we would cover, and the space is not necessarily oxide and non-oxides. So we did a PCA analysis to see, to map on a 2D systems where the data were, and in the end, it turns out that in the region where there were many data, even if they were non-oxides, the error of the machine learning was small. And in the region where there were few data, be it oxides or not, in that case, the error was big. So it's not obvious to see the kind of bias that you can have. One possible thing that you can do is to try to develop a machine learning model that also predicts an uncertainty on the prediction, so that then you know the kind of confidence that you have on the prediction. That's the best that we can do, I think.
Okay, thank you. Luca? No,
okay, it was actually the old end, but I can add on Gianmarco. At the end of the day, estimate the uncertainty. Conceptually, it cannot be done in every case. It's really like physics. At some point, you have things that you have not yet seen. So you have no idea. You have a prediction, and you have some kind of built-in uncertainty if you did think properly, but you could be very well surprised. And you have no indication that you might be surprised unless you check, right? Well, I mean, if nobody saw that when you go to very high velocities, speed, you break Newtonian mechanics, nobody would have imagined that then you check and indeed you break Newtonian mechanics, right?
Course.
There is no,
of course, but at least, I mean, I mean, from what we did, we published a paper about that. Actually, when we do several models, we do an ensemble of models out of the data, by changing the data, changing the models, then you can have a range of what you have. And we saw that when we had points that were further away from the other. So when basically we were doing more extrapolation than interpolation, as Matthias was writing in the first question, when we were moving towards extrapolation, where you have few information basically in the data set, then we would see that the uncertainty was increasing. So that's already a sign.
Okay. Good, I think.
Just to reiterate a somewhat trivial point, but in all of this, I think it's important to keep in mind that I think what we're talking about here is the uncertainty associated with the machine learning training.
Yes.
So if we establish this would tell us sort of how much uncertainty we're inducing by training a machine learning model. It would not tell us anything about physical accuracy. I
fully agree.
And I just wanted to kind of raise that point because I see these things confused all the time.
Okay. I have to say,
in a similar spirit to what Chris said, but let me see if I can put a slightly more optimistic spin on it. So once one's trained a model on a collection of data, you can then use that model to go and do something new. If it's a potential, you can go off and run some dynamics with it. And then you can take samples from those new dynamics and check how consistent they are with the method that generated the original data. And if you go around that feedback loop sufficient times, you should be able to iterate closer towards self-consistency, and then you can be confident that for any situation which you encounter during routine use of your model, you should have a good description of the underlying physics. But it's hard to get complete confidence in that, of course.
Yeah.
New things can always happen.
No, that's exactly. I mean, that's why I would say at the end of the day, to decide if a correlation is just really a correlation and say physically wrong, or if there's a physics behind it, you have to go back to the old way of doing science after you have done the machine learning. Now, actually, I have several more questions, but I see actually we are running out of time. As you see, actually, the page is only actually 1/3 full, but I will not really put the other questions in. I will probably place them at some other point in the conference. So I think I like to close today's session. I thank really the speakers and everyone who joined the discussion very much. I think we had a quite, I would say, exhaustive day today, and but also very interesting. So thank you very much, the speakers of the last session, and thank you very much everyone else. And see you tomorrow morning.
Thank you. See you.
Thank you.
Thanks everyone. Bye. Take care.
Thank you to everybody.